In this lecture, in module 2 in lecture 17, we will discuss about new generation offshore structures. In the last lecture we discussed about the analysis and some of the design implications of compliant structures along with the derivations of mass matrix, stiffness matrix and the damping matrices using Rayleigh damping. We also compared the influence of different kinds of damping matrices with Cauchy damping, etc. So, as we understand that once the deep water oil exploration starts moving towards greater water depths, when the oil exploration starts moving towards greater water depths, so your structure should be enabled to counteract the lateral forces by its geometric assembly. So, a structure should be capable of alleviating the lateral loads by a new geometric form. Therefore, as you move towards greater water depths, you should have a structural form which actually adjusts itself for catering to the additional loads which are coming because of the greater water depths. So, we are now looking approximately the exploration in the present trend at the water depth of 1200 to 1500. It is expected that we will go the depth of exploration even 1500 to 2200 by 2015 year, because the resources of hydrocarbon have started moving to a deeper waters. Therefore, the conventional platforms, of course what we have in ATs, jacket structures, are totally obsolete now. They are of no use at all for any kind of new exploration. Okay. So, we are looking for new trends of offshore structures where most commonly people have started using FPSOs, and of course for exploratory drilling people start using drill ships, etc. But all these structures have their own limitations of positioning them for rough sea states. So, we would like to go for a permanent installation like a structure or an offshore system which can be installed permanently in a location for a period of let us say 5 to 10 years, and which can also counteract the lateral loads in rough sea states at greater water depths. So, we are looking for new generation offshore structures which we will discuss in this lecture, where we will also touch upon the dynamic analysis of this in this lecture. So, if you look at the new generation TLPs, even tensional platforms have also moved to deeper water depths. So, two interesting forms have been arrived at. One is what we call as Moses TLP, another is Sea Star TLP. Both of them are advancements in geometric design. You can see very well here from both the figures that the Moses TLP has a ring pontoon. The pontoons are not provided at the cover or at the circumference, they are provided at the ring closer, which is the ring pontoon type. You can see here the pontoons are located here, not on the periphery. Usually TLPs had pontoons on the periphery. So, it is a ring pontoon type, and of course which has got a centralized column hull. The column hull is centralized, and if you look at the Sea Star TLP, it has got further advancements of having only one central column, and of course the legs are spread out. So, these are all interesting new form generations which has been done for enabling the capability of these platforms for taking it to deeper waters. Of course, they are all tension leg platforms. You can see here the teethers which are holding down the column members. These are all teethers what you see in this figure as well as here and so on. So, they are teethers, so therefore holding it down, and this has got some geometric advantage compared to the conventional TLPs which has been built in early 80s and late 90s in Gulf of Mexico in majority for oil exploration. Of course, in first module in the lectures we have given you a detailed statistics of different kinds of TLPs constructed all over the world till the year 2012. Interestingly, people have moved further forward for greater waters other than what TLP can cater. So, buoyant leg structures has become a very interesting and innovative application in offshore platforms. As the name suggests, each leg will float on its own self buoyancy, that is why they are called buoyant leg structures. Interestingly, only one platform has been constructed so far successfully, which is again on a trial basis, which I will show you now here, based on which a new geometric form is attempted to be evaluated in the latest research. We will see that what is happening here. Before that, let us try to understand what BLS mean. BLS actually are tethered spar. Buoyant leg structures are nothing but tethered spar with a singular group of cylindrical water piercing hulls. They are expected to be an alternate successful structural form to TLPs and spars, that is what literature project them. They are essentially positive buoyant structures. Positive buoyancy means the buoyancy will exceed the mass, as we understand in case of TLPs also. Therefore, they have got to be held down to the foundation of the seabed using some external restraining arrangement, usually it is tethers. Okay. The positive metacentric height of this kind of structures is essentially maintained in the design. You can always maintain the metacentric height to be positive or negative with respect to the center of mass, depending upon your mass distribution on the superstructure and the hull. So, you always maintain a positive metacentric height to ensure a desired stability even after the removal of tethers. That is a very important aspect here, because in recent times in literature you must have studied by this time, there are many cases where there has been pull out happening on tethers, especially in TLPs and guide and moved towers. The tethers gets pulled out, not plugged out, they get cut because of marine trafficking or because of impact of vessels or barges on the platforms, etc. So, whenever a tether gets pulled out or pulled off from the connection, then it is expected that a positive buoyant structure will always tend to lose its stability. So, one of the important aspect in present research focus is that in case if the removal of tethers happen, will the structure remain or sustain its stability as a positive buoyant system. So, that is one important aspect which we are deviating completely from a conventional platform like jacket structures to that of completely floating structures, because they are not ships or they are not FPSOs, because they are moved using a dynamic positioning system on a temporary location. Of course, operational sea state for FPSOs and drill ships are entirely different from what we are looking for a permanent system like this. Okay. So, in case any critical sea state is being expected to arrive at a specific sea state, then FPSOs or drill ships are made non-functional. Of course, they will sail, but they will not be producing or they will involve in production of the system. Okay. Whereas, in these kinds of platforms there is nothing like a dynamic positioning system, it is a permanent, or you can say more or less a semi permanent installation which has to cater to rough sea states even when they are fixed, and we are talking about a system which is going to work at greater water depths. Okay. So, the one of the important focus of this kind of research as instructed in the literature is that even though you have got a tether pull out happening in these systems, will the system remain self stable and floating or will lose stability. So, that is one important aspect. Therefore, in most of these kinds of innovative forms it is expected that your analytical, numerical and experimental should focus on what we call free flotation analysis. Okay. This has been an important focus now in dynamic analysis. In case of deep water offshore systems or ultra deep water offshore systems, which has not been a focus maybe about 15 years earlier. Okay. We are looking for free oscillation studies, maybe experimental, maybe numerical, maybe analytical, depending upon what model are you generating. Okay. Because the focus is I want to check whether the system will remain stable and position restrained or at least stay in position even when the tethers are completely plugged off. So, there are one more derived advantage by looking at this kind of analysis stability. The derived advantage is, if I have got a system, let us say this my sea, this my seabed, this is my system, maybe a black box which is self sustainable even when there are no tethers plugged to the restraining system. Okay. So, one derived advantage of this kind of system is that I can easily tow this using a barge. So, the installation becomes very easy in this case. Okay. In such kind of systems which is remaining self stable without tethers being in position can be easily towed. So, the installation becomes easy as well as decommissioning becomes simple. Also is simple. So, there are two derived advantages they get by making the system self stable even though when the tethers are plugged off. Of course, as we understand, since the structure is having positive buoyancy, to make the structure to have a specific design draft, you should be very careful in imposing a T to the cables so that the weight and T are adjusted so that the design draft is achieved for a specific position of the sea state. Okay, to hold it permanently in position, I need a dr, and dr will be achieved only by imposing T naught, remember that, because it is a positive buoyant system. Okay, otherwise it is free floating. So, the towing, installation, commissioning and decommissioning becomes very easy compared to other kind of old generation platforms which have been a Herculean task, especially for example in case of jacket structures, gravity based systems, they have been very difficult. Now, this system has become more comfortable. Therefore, our dynamic analysis should also focus on this kind of studies if you really want to promote new generation platforms for deep waters. So, deep draft and high stability of BLS, which is indicated in the literature, I will show you the references later, results in a relative insensitivity of these kind of structures for ultra deep waters. That is one of the important attention why BLS or buoyant leg structures are carried forward for new generation platforms, because the deep draft and high stability of these units make it water depth insensitive. So, you can carry to any water depth you want. It is expected that one can carry to any water depth. Okay. Is this clear? So, one main focus in case of new generation structures is that I want to make the system self stable, positive buoyant, deep draft and highly stable. And BLS is one such example. Of course, the innovation does not stop here, it has started in recent times. You will see the papers we show you now are all only about 1 or 1.5 years old, just published in the literature. So, people are now looking at this kind of platforms. Of course, the concept of using BLS for production and drilling started only in the year 2005. Okay, first paper was projected by an author in one of the ISOP conference in Japan. I will show you that. So, it started only about let us say 6-7 years down the line as a concept, but verification of this concept on a geometric form, experimentally, analytically and numerically analyzing it dynamically and see whether they are stable or not, these are all only about 1 year old. So, it is a new generation platform relatively compared to any other established platforms. So, obviously, your question of asking me whether such platforms have been installed is having no meaning, because still it is under trial. So, BLS being a deep draft structure, it reduces the exposed structural part near the free surface, that is a great advantage what we have in case of deep draft structures. So, therefore, obviously this reduces the lateral forces on the structure in comparison to that of a TLP. Okay, that is what one can immediately summarize when you have got a deep draft system. The other advantage what we have in case of BLSs are, I can have a moon pool of a BLS where I can put my risers through it, therefore, the risers are also protected against the lateral forces near the free surface, because free surface is the area where the wave forces are maximum. Okay, we understand, we know that, therefore, risers can be protected at least near the free surface elevation of the sea, therefore, risers will attract less forces. Of course, these advantages were there in earlier conventional platforms also. So, as I said, the geometric form invention started getting merits of the previous platforms and overcoming the demerits of the older platform, that is how it has been done. So, looking into the concept of integrating tension leg platforms into buoyant leg structures, a new structure was proposed which people have addressed as tension buoyant towers, and they were designed and they were tested. Okay. So, tension buoyant towers were designed essentially a amalgamation of BLS onto a TLP. So, that is the tension buoyant tower which you see here, which has been developed and designed by Horton Wilson Deepwater Systems Incorporation US. So, of course, the references are I think in a very small size, you can see it in the web at least to be in a larger size. So, Halcott et al. Has first given the design of this in 1991, which has been published in an OTC conference in Houston in Texas. Of course, in 1995 Robert and Kopanolu has given a concept of BLS to be extended for deep water offshore structures for production facilities. So, this is a classical tension buoyant system which has been numerically analyzed, not constructed, numerically analyzed by Halcott. So, BLS had the following advantage of spar because of its shape, because you can see it is shape resembles to a classical spar and it is a deep draft feature. Of course, it resembles to the behavior of a TLP because the tether restraining system, it has got a tether restraining system, and these are all the satellite subsea wells which are going to support this. The only demerit what this kind of platform had, which has been proposed by the inventor, is that the platform is suitable only for leftover and marginal fields, it cannot support larger fields because obviously this does not have storage capacity. Okay. So, it supports only the leftover or smaller fields, but the advantages are very serious in terms of TBTs, tension buoyant towers. It is a deep water generation, new generation deep water structures, easily relocatable, you can install it and decommission very simple, and it is very easy to fabricate and install. So, these are the two major advantages. So, for your understanding why we are bothering about the fabrication and installation and decommissioning, in a total cost of offshore installation, for example, in a total cost offshore installation which runs of course in 10 power 5 billion US dollars, about 25 to 30% of this cost goes on installation. I should say installation alone, it is a very amazing figure, it is a very amazing figure. You have only countable number of contractors can execute installation of deep water structures in Gulf of Mexico, very few, very few. So, they have monopoly. It is not a disadvantage, it is an advantage because the technical know-how of installing a system in deep water is a patented right on these kind of contractors. So, they charge approximately about 25 to 30% of the capital cost capex of this installation only for installation. So, if you really want to reduce this cost for deep water systems, I must think about a system which can be easily towed and installed. That is why the primary issue focused on new generation platforms for how they can be simply towed and commissioned. So, TBT came into play and tension buoyant towers had shown these advantages. Of course, no papers and no literature will give you a cost comparison of any of the installation platforms in the world. No paper will give you a commercial touch on this, what we are talking about only in engineering perspective of these platforms, but it is very clear in some of the financial aspects of these platforms. You will read from the papers that about 25 to 30%, 1/3 of the cost of the capex cost of the platform goes purely on installation and commissioning. It is not that simple a figure. So, this was proposed in about, let us say, down the line about 15 years back, which was a concept. You can see it is a numerical model, it was a concept not constructed. Subsequently, a platform was attempted as a tension buoyant platform. The first buoyant tower CX-15 was loaded out in the Peru's Coronimo offshore field, which has now become a promising figure, which is going to now produce oil end of 2013. It is a new platform which has been constructed recently, which is commissioned now. There are other innovative offshore generation structures which are now available in the literature. The innovative geometric form of course is understood to be having improved motion characteristics which can suit deep and ultra deep waters. So, some of the classical examples what people have attempted in the literature is, one is what we call non-ship shaped FPSOs. Now, one may wonder that why a ship shaped FPSO may not be a successful model, because FPSO stands for floating production storage and offshore facility or offloading facility. So I have, it is a floating facility essentially, it has got production facilities as well, it can do drilling, can store, it can offload also. For example, you have got a barge, can keep on transferring the extruded oil onto the barge and keep on offloading it to the shore. So it has got all facilities involved. So essentially people thought that the unused barges and ships can be converted to FPSOs because ships have very high, strong, favorable flotation characteristics for which they have been designed. So people have converted, modified the existing ships, commercial ships, not the passenger ships, commercial ships, the hull has been remodified and they started using it for FPSOs. But they saw that there are some specific flotation characteristics associated with ships which is related to head sea condition which affects the production in case of rough sea states. So people thought, why do I have to have a longitudinal hull or a lateral reduction hull, why can't I have a circular hull which can approximately represent a common dynamic analysis characteristics for all approach angles of waves. So people said I will go for non-ship shaped, not necessarily circular, non-ship shaped hulls of FPSO. That is one of the recent generation platforms people have attempted. The second of course is a triceratop. Triceratop is essentially about, let us say 700-800 years old species of an animal which has got a specific characteristic of very high positive buoyant system. Okay, it's like looking like a kangaroo of a very large size. It has been some people name it as a dragon, some people name it as a fly, etc. It is having it's a very massive structure, rests on 3 legs, the one in the center and the two hind legs. So it is a very interesting and very massive animal. So triceratop is one of the important configuration which has been arrived at based on this geometric biological species. The third one is again a very interesting form which is called MinDock. Okay, MinDock is another kind of platform which is now emerging for deep waters. So this is one of the interesting Sevan Vågøy which is now located in Norway, in Eihaven, Norway, which is circular FPSO. It is an FPSO which is having a circular hull which is now located in Norway, which is now doing for oil exploration. I think you will appreciate that Norway is coming out an alternative renewable energy source and they want to make the country completely on renewable energy, alternate renewable energy by year 2020. Okay. So it is a new kind of platform which is coming up, not for oil exploration but for shale gas, etc. The other one is again a non-ship shape, of course a circular hull, it is called as a Goliat. It is the first oil field developed in Norwegian sector, it is a cylindrical FPSO. So the production is due by end of 2013 again. It is again a ship shaped FPSO, non-ship shaped FPSO. The third structure is what we have originated in our studies here, which is again a concept from Triceratop. The Triceratop concept was first floated by White et al in 2005 and he said yes, this platform can be used comfortably for the deep water oil exploration because there are some structural advantages which this platform has. Let us say what are these advantages quickly as we go through this presentation. It essentially consists of a deck which is having the same topside detail as that of a conventional platform, and of course the tension buoyant leg structures. The buoyant leg structures are what you see at the bottom, which are groups of BLS which has been anchored to the seabed using tethers, therefore these called tension buoyant leg structures. Of course the BLS and the deck are connected interestingly by a ball joint here. So the ball joint connects actually the deck and the BLS. The greatest advantage by this form which has been derived from an articulated tower is that in case of any lateral load coming on to the BLS because of wave or current action, the BLS are not interconnected to each other. So each one of them have a freedom to move independently. Okay. This independent motion essentially in terms of rotation will not be transferred to the hull because of the ball joint. So the ball joint observes the rotation from the substructure to the superstructure in case of rotational degrees of freedom. Similarly, when the hull starts activating or rotating because of the aerodynamic forces, wind action, that is not transferred to the BLS. It means certain category of forces and displacements in terms of rotation are isolated from the dynamic characteristics by introducing a disconnectivity between the BLS and the deck only in rotational degrees of freedom, whereas in displacement degrees of freedom like surge, heave and yaw sway, this holds as a rigid body. Okay. So, the advantage is, as we already see, there are distinct categories of frequencies as far as TLP is concerned. Similar here, the response characteristics are isolated. So, the rotations are not transferred, but the displacements are transferred 100%. So, it becomes a rigid body motion. Okay. Now, what is the great advantage we achieve by introducing this kind of disconnectivity in rotation degree of freedom? The most uncomfortable region of working for a deck or a people on board on deck is that rotational motion. In case of heave, the heave displacement being tether restraint system is relatively very low, okay, but the differential movement because of this wave action with respect to any rotation, maybe pitch or maybe roll, is phenomenally high because surge is very high. Okay. So, this rotation will always cause uncomfortability to people work on board, as well as it can cause lot of risk to the riser systems connecting the subsea to the superstructure or the hull or the deck. So, to avoid this kind of rotary motions on the deck, so this rotary motion has been isolated from the substructure or from the BLS to the deck using a ball joint. So, the ball joints introduced between the deck impose structural advantages, which can be seen from different papers here. Some experimental investigations have been carried out on the scaled model to show some salient advantages of this with respect to other conventional offshore structures, which we will see. There are some distinct advantages of this which are derived from the experimental studies and analytical studies done. They have got better motion characteristics, so therefore they are suitable for deep waters. It has got improved dynamics in comparison to TLP, we will see that some of them now. The wells are within protected environment, laterally supported. It is a simple structure, simple station keeping is required, easy to install and so on. The whole structure can be reused, okay, that is very important, and relocated. It has got a very simple restraining system compared to that of a TLP. It is a very highly stable structure because I will show you how the free flotation will help us to enable or to ensure the high stability even when the tethers are pulled off. Relatively low cost because I am talking about saving of this cost in installation. So, essentially to impart or to understand the free flotation characteristics, free oscillation studies have been conducted on this particular platform in a scaled model to understand the installation complexities of this new geometry. A scaled model was investigated. This was the model considered with a triangular deck on the top with 3 legs, that is why it is called triceratops, and you have got the BLS on the top, and then the hull or the deck is connecting the BLS by an hinge joint, and the BLS are anchored to the seabed using tethered or cable systems. So, these are the two figures will show you the ballasted BLS, because I want to have the installation of the BLS proper in case of flotation. So, I am ballasting the BLS at the bottom here, you can see these are the ballasted BLS, these are the ballast being used. This may draft level which is supposed to be, these are my ball joints which are elaborated or highlighted here. So, this is my ball joint, you can see here the outer cover is made out of HDPE and this is threaded, this threading is connected to the deck, and this ball joint is isolated in terms of rotation with respect to the substructure of the BLS. This is an installed model in the wave flume. I will show you some of the videos very quickly at the end of this lecture. Interestingly, if you look at the natural periods of this platform when they are not tethered off, okay, the heave has got about 20 seconds and the roll and pitch also has about 20 seconds, whereas in conventional TLP you see the heave periods are varying from 2 to 5 seconds. It means this structure is considered to be relatively flexible compared to a TLP in a stiff degree of freedom, because these are all stiff degrees of freedom, heave, pitch and roll. I am not talking about surge, sway and yaw which are otherwise flexible degrees of freedom. We are talking about the heave and pitch and roll which are considered to be stiff degrees. The stiffness in these degrees of freedom are relaxed by introducing a ball joint. Even when you pull off the tethers in flotation, this gives me a period of about 20 seconds. Now, you may wonder what is the beauty about this in terms of installation. The free floating periods are very well away from the wave periods. What does it mean is the wave will become insensitive, because the wave periods are generally varying from 6 seconds to 20 seconds, maximum is 15 seconds, but my period is around 20. So, the platform is expected to remain stable under free flotation conditions. Free flotation means ethers are not connected to the seabed, they are freely floating, remain stable. But of course, you have got to take care, because during commissioning you have to impose T0 on the teethers. So, its free flotation periods are very high, therefore, you have got to take care of while installing them in the sea state. And also interestingly, if you look at the damping ratios, which is closely only about 1.3% to 1%. So, the damping is relatively low. What does it mean is instantaneous decay of response will not occur, okay, which will also cause material degradation and material loss to the deck or to the BLS if the damping is very high. Okay. So, damping low means it will come to rest, but slowly. And of course, the results have been compared analytically and experimentally and computationally, and you will see there is a close agreement, at least in the periods. In the case of damping ratios, the one what you get experimentally includes hydrodynamic, aerodynamic and structural, all the three, whereas analytical is a Rayleigh damping. Okay. There is no hydrodynamic characteristic into this, therefore, there is a variation in the results. Okay. Interestingly, a numerical study was also done on this platform using ANSYS Aqua. I will show you some of the steps how this ANSYS Aqua was carried out. So, in the first step, the coordinates were introduced by creating nodes. You can see here these are the coordinates manually given as an input in ANSYS Aqua to create the nodes. Once the nodes are created, then you have to create the line elements from the nodes by joining them to create the members. Once the line elements are created, then you create the deck using a surface modeling as a deck meshing. Once this is completed, now you have to separate each one of the BLS independently. See that there are 3 kinds of structures, rather there are 4, one BLS1, BLS2, BLS3 and deck. So, there are 4 independent units, 1, 2, 3 and 4, 4 independent units. So, one can easily measure and see the dynamic response behavior on any HC condition for this platform independently on each of the legs, and you can see whether which leg will fail first, if at all it is failing. Okay. They are not connected at all, they are independent, and there is a reason why they are made independent, because the legs, the BLS are made independent because there is no connectivity between them. The deck and the BLS are made independent because there is a ball joint in between them. So, the degrees of freedom for the BLS and the decks are different. So, the platform is analyzed using 9 degrees of freedom model like this. My mass matrix, I am partitioning it, this is 6 by 6 and this is 3 by 3. So, I have a mass matrix of 9 by 9, this corresponds to BLS, because in the CG of the BLS I have all the degrees present. Corresponding to the deck I have only 3 degrees present, which are only the rotations, because the rotations of the deck are independent of that of the BLS. Okay. Whereas the displacement degrees are common in both cases because of rigid body motion. So, easily I can find out the mass matrix of the substructure, that is the BLS, and the mass matrix of the superstructure, that is the deck, independently in these 9 degrees of freedom. That becomes a mass matrix. Similarly, K matrix will also have the similar concept. Again partition, this is 3 by 3 which is for the deck, and this is 6 by 6 which is for the BLS. Okay. Should you be interested, we can explain this derivation in detail in other lecture, but anyway I will give you a reference, you can read it from there. Now the reference available online, you can read it from the reference. The whole derivation of mass matrix, stiffness matrix and the Rayleigh damping matrix available in the paper directly, you can see it from the paper directly. So, they are made independent. You can see here there are 4 system units here, one is BLS1, BLS2, BLS3 and deck, they are independent. Okay. After creating this, then the water depth details are given. Now, this model has been analyzed to to start with at a depth of 600 meters. Of course, this has been tested at a depth of about 1500 meters also, but the results what we show here is only for 600 meters. So, you have to manually enter this value for analysis. Once this is done, then you have got to specifically enter the values of center of gravity, mass of the structure and radius of gyration, which you can calculate mathematically once you know the m, rx, ry and rz values for the given geometry. Okay. So, this is what we have entered here. So, in the aqua details of the point mass you have got to enter these values, and this is the point where the CG of the system will be now entered for the BLS, and CG of the system for the deck will be entered in the top separately. And then the mesh is being formed for the BLS as well as for the deck. This is how it look like. This is what you see here is the CG of the superstructure, which is nothing but the center of rigidity of the lateral forces acting on the body also, because of the top side details. Top side details are not shown in this model here, but they have been made, and then you can introduce this center of rigidity, which is because of the lateral force acting on the top side details. Then these are the wave directions which for which the model will be activated to. Once this is done, then this is how the developed model will be anchored to the seabed looks like. These are my principal directions of x1, x2 and x3. This is my closed view of the model. You can see here the ball joint being connected with that of the BLS and the deck here. So, each one of them have independent coordinate systems x1, x2, x3 and so on. Okay. So, they are independent, so one can measure them separately. After understanding this, how the model will be installed in depth of minus 600 meters with 0 as MSL. This is a closer view of that. This is my wave direction. So, therefore, you can see the instrumentation on the top for experimental analysis. Instrument accelerometers of A1 etc. has been kept, one on the CG of the deck and one on the BLS to compute the relative motion between the BLS and that of the deck independently. These are all triaxial accelerometers which can measure the surge and sway depending upon what you want, and incremental will give me the differential rotation. Okay. So, these are the results what we have. You can see here that for every degree possible 0, 90, 180, of course 30, 60 and 45 are not available here, but some of the reference I will show you, their results are available in that. You can see here that the analytical studies what you see at 0 degree and experimental 0 degree, which is grey and white, you can see they are matching, you can see they are matching, okay, you can see they are matching. So, there is a close agreement of the results analytical and numerical. Of course, there are variations in experimental results marginally, because the points what you see here are all experimental results marginally, they vary. So, some quick conclusions from this what we have shown you are, due to the presence of ball joint, the rotational response of the deck is far lesser than that of the BLS. There is some influence on the deck having in heave response 90 degree, which can be due to the differential phase lag of different BLS, because they are independent each other. The experimental, analytical and computed periods closely agree. The surge and heave periods of Triceratops are higher in comparison to of TLP, it means the system is flexible. Though remember, interestingly, the T naught of the stiffness of the tether is same as that of TLP, that is a very interesting factor here. The stiffness or the axial stiffness of the tether remains same as that of the TLP for the water depth, but still the system becomes flexible. Okay, that is one of the important advantage which will avoid pull out of tethers under severe lateral loads. Therefore, this platform can be carried forward for ultra waters, that is advantage. Okay. And you can also see here, because of heave restraint system, the platform is generally not influenced by wave directionality, as we see most of the results are almost marginally similar to each other. The pitch response of the deck is much lower compared to the BLS, which tells me very clearly that there is no transformation of rotational responses from the BLS to the deck or vice versa. The proposed platform shows more comfortable working. I will show you a very interesting video which will realize that the rotation of the BLS does not transfer to deck at all. Physically you can see it in my video. So, there is a good agreement of experimental results which will show that there is a possibility of modeling this with the proper or appropriate values of damping on the hinge and the friction damping imposed by the ball joints, okay, because there is a close agreement. Some interesting references which you can read, Minu Patel on complaint offshore structures, and you can see, I mean, it is very interesting that only we in IIT Madras made research on this. There is no other paper available on the net today on Triceratops, no other paper except what we did, except only one paper of conceptual what Professor White had told in 2005 in one of the ISOP conference. That is only a concept. There are no references available for analytical, experimental, numerical investigations done on this kind of new generation platforms for ultra deep waters. This is the paper what Charles and Kopanulu said in 2005, that a concept of Triceratops can be attempted for ultra deep waters. It is only a concept introduced. So, this was patented, technology transfer has been now done, and we are trying to push this forward to places where ultra deep exploration happens in the world. Okay. Of course, it cannot be done in India because we do not have oil exploration happening beyond a higher depth in India. So, we are looking for a depth where the installation or the exploration depth is approximately 1.5 kilometers. So, we look at the video. You can see here for a long period waves, you can see the rotation, independent rotation of the BLS, whereas the deck almost remain horizontal. Okay, the deck is almost, there is no yaw motion, there is no roll and pitch motion. Of course there is no roll motion happening possibly, so unidirectional wave, but there is no pitch motion happening, and this is true in the case of long period waves also. This is a long period wave now, the other video is running now. You can see here the relative motion in heave direction, the draft variation does not bother the deck at all. Okay, that is a very interesting understanding which has been verified experimentally, numerically and analytically for this kind of new generation platforms. So, if you have any questions, we can answer them quickly. So, this will be the last lecture as far as module 2 is concerned. We will talk about module 3 from the next class onwards, where we will talk about advanced applications of dynamics on offshore structures, where we will talk about stochastic dynamics applications. Then we will talk about response reduction using hydrodynamic response reduction using perforated cylinders, etc., and that will maybe around 5 lectures maximum in module 3, which will address some of the advanced topics related to dynamics of ocean structures. So, new generation platforms are on the move. People are looking for geometric innovativeness, shape geometry innovativeness. Of course, people are also working on material innovation like light buoyancy materials, etc. That portion anyway is not discussed in this scope of the lecture at all. People are also using different kinds of materials. Okay, we are not looking at that here.